This is tutorial number 7, which deals with performing finite element analysis in the 3D Experiences platform. I want to remind you that the Abacus program is the main solver for 3D Experience for the past 15 years. I came across this concept or this title because of the paper that you see here. And it's dealing with a wind turbine tower, and it does many steps. It starts with a linear buckling analysis, then it goes to uh, uh, performing the same analysis, but not linear buckling, but with material nonlinearities only. And then there's a follow-up analysis, which does the geometric nonlinearity and material nonlinearity. Now, that paper was reviewed by the YouTuber that you see here, and he is using a free software called Pre-Po Max package. Okay. Now, the tutorial that you see now, this tutorial 7, is going to go into this playlist. Okay, but I have already done the linear buckling analysis of the same problem and stored it with 3D Experience and stored it in this playlist that you see here. The first one, tutorial 11, I actually constructed the geometry, reconstructed geometry based on the information that's given in the paper. And in tutorial 12, I actually imported 2 STP files from the work of Dr. Wagner, the very last, or the YouTuber that I showed, and just started with that. I did not reconstruct the geometry from scratch. So here's the situation. In tutorial 11, I did multi-section solid of these layers, but in tutorial 12, the entire STP was the 2 of them, one for the tower, the other one for the flange, and these are the thicknesses associated with different layers. So in order to do that, I actually did a little bit differently from how it was done in 12. I actually because I did not want to mesh this whole thing as a single piece, as I did in number 12. What I did, I ended up extracting the appropriate hatches and then assign section properties and mesh them one by one. So that's why I have a lot of extracts, and then for example, I extract the bottom 4, or there's 4 here and there's 4 below it, 8, the bottom 8 patches, and join them. Okay, and that will give you my first essentially join 2. Okay, 17 millimeter, and then this 17 millimeter I can assign thickness to it later on with shell element, and I can mesh it. And then I extracted the next 8 layers, 16 millimeter, and joined them. And then directly I can apply material to it. The materials are the same, but directly apply thickness to it and then mesh it. So that's why you see many extract, 1, 2, 3, 4, 5, 6 joints, and then each one meshed and assigned section properties. Now this is the place where those STP files can be downloaded. I have already downloaded them, so I'm not going to go there. I've already done that. And we're going to assume that material behaves non-linearly as an elastic, fully plastic material. However, the author of that YouTube video indicates that yes, you can use elastic fully plastic, but he's doing it a little bit differently, although I'm not convinced that it makes a difference. But it's he's arguing that because of the convergence issues that you may have with elastic fully plastic, he's giving a very slight tilt of that fully plastic slope, basically. And he's using a million, I use a million. That's irrelevant. This number is a dummy number. Now, there are two load cases that are being considered in that paper, and uh, the two papers that are being considered there, two load cases being considered there. I'm only doing load case two, okay? Load case two, which is applying, first of all, the full weight, self weight. There is a vertical downward force at the very top. That's because of the structure on the top of the turbine. And then there's a shear force there on the very top, okay? That is because of the aerodynamic load that is exerted by the wind, or by the wind, by the rotating blade on the blade itself. There is a torsion, and there is a moment because of the bending of the tower. Okay, so I'm going to be doing only this load case, and this is the details of what's given here, as I mentioned. Because we're doing fully plastic or elastic plastic analysis, I need to know yield strength. It's right there. And this is all the loading information above. We need the density because we need the self-weight. And in fact, these are the things that I used already in tutorial 11 of the buckling analysis, 11 and 12 of the buckling analysis of the wind tower. This is excerpt from the paper, and this is the graph that's generated. So for us, we're doing the load case two. This is the load case two. We're not worried about these things. This is for material nonlinearity alone, material nonlinearity analysis. One for the load case one, which I'm not going to look at. I'm going to look at load case two. So whatever I do, I have to compare it with this dashed curve. Now, when it comes to meshing, because these are six joints that I have to mesh for each, the layers with the same thickness, I'm going to use parabolic first of all, mesh size 100. These are the same numbers that the YouTuber is using. And because at the interface of these joints, there will be maybe duplicate nodes I have to merge them. I'm going to merge it. With any two nodes that which are within 10 millimeters of each other. Now, this did not have to be done in tutorial 12 of the buckling, because I joined the whole thing and then meshed it. But anyway, here I have to do that. Now, for example, this particular one joined to 17 millimeter, you apply 17 millimeter thickness to it. And these are the details of the analysis. I'm going to use these numbers. Make sure that the NLGeom button is off, so that we only do material nonlinearity. And I'm going to kill the job at around 83%, because this thing keeps going on and on and on. And I killed it at 83% and looked at the results to that point. I just pointed out that this is not done in tutorial 12 because, well, we can look at it. Now, when it comes to plot those plots, I have to first of all request the deflection plot for the very top node, top reference node. I have to ask for the reaction or force plot at the very bottom node, which is clamped essentially, and then using the facility that's inside of a 3D experience, I can combine these curves and do manipulate them. There's a lot of Excel work that's done in Dr. Wagner's YouTube video, but that's unnecessary because I can do this thing by the software. Yeah. This is the manipulation that I was talking about. You have to normalize by dividing it by some number, etc. These can be done. All right. So let's go to 3D experience. We're already there. Let's go to the software right there. And I'm in part design. Okay, because we'll be dealing with surfaces. Later on, I have to switch to generative shape design. Okay, the first thing I'm going to do is to switch to generative shape design or another application that you can actually do basic surface operations, but I have generative shape design, so I'm going to go there. All right. Next thing I will do, this is going to be my file, but I'm going to import those two step files. Now, when I import it, it doesn't go into this file directly. It opens up by itself. I'm going to copy and paste the stuff that I want from it. So let's go ahead to here, this one, import. I'm going to import my tower step file and my flange step files. I have already put it on my disk drive, imported that and put it on my disk drive. You can see that this is tower step, and I put it in some folder there. So I say, okay. Give it a few seconds. There we are. Close this and close that. Notice that this is where I do my operations. This is where it's got imported. Okay, and then another import. So we go there, import the flange. So I change this thing. Yeah, file on the disk. Oops, actually, let me go there. Flange right there. Say okay, and say okay. So another file will open up, and that one is going to be the flange. Okay, so what I will do is I go to this and copy the geometric, notice that the first one, the flange, this is the tower. So I'm going to copy geometric set, copy, go back to my original file where I'm going to do all the calculation, and I'm going to say paste. So I guess I have to put it there on the 3D part, paste, right there. Okay. This is the tower. First surface is the tower. You can see that right there. And then I go to the other file and copy the surface here. Right click, copy, and go back to my original file and then save it in geometric set. Paste. There's the flange. You can see that. All right, I don't need these two other files, so let me just close them. I don't need them. And don't need this. Everything is in that file where I'm going to do all of my calculation. So right away, I'm going to save this. Good. Now, here's the plan. What I want to do is first of all, first thing I'm going to do is to join these two. This join one, make it a little bit easier for me to proceed, but it may not be necessary, but I will join it. So here is join. I join this first tower and the flange, and I say, okay, there's my first joint. So what you see there is in the tree is guy. Okay. Then I'm going to start extracting the bottom 8 patches, and I'm going to join them because those 8 patches will have the same thickness. Okay. So how do you do this thing? Let me turn this thing around so I can see it easier. Okay, where is the extract? So let me go to surface tab. I'll see that there, essentials. It must be somewhere here. The extract icon, oh, right there. Extract this. Now, I don't want to do any propagation because I want individually pick them. So let's start from the bottom. Here is 1. There's 2. Oh, notice that it won't pick it. That's because if you're doing it like this, you go to that bag here. See that bag? And then you can start picking. Okay, good. I can do it here. I can do that there. Then I'm going to turn this thing around until I see the other side of it. That guy and this fellow, that guy, and let me zoom in, this fellow. And notice that I'm going to say okay. Okay, see that? I have extracted these 8 faces, and that's what this thing is. And I'm going to join them and call it 17 millimeter. Okay, so where's the join? I can do it from the tree, from here, all the way to there. And I'm going to give it a name. Let me see if I can name this thing. Yeah, we can name it later. Elements to join. We say, yep. Say okay. And I'm going to call this thing properties. I'm going to call this thing 17 millimeter. Oops, where's that thing? Not that. The cancel. Properties, right click properties. Yeah, right here. On the feature properties, I say 17 mm underscore. So this is going to be the 17 millimeter set of patches. Now I repeat this thing. I'll do one more and then I stop the video and do the rest. I want to remind you. Okay, so let's go ahead and do this again for the next layer. But I'll stop the video because this is a lengthy process. So I'll stop it, go and do it, and when I'm done, I'm going to come back and we go from that point on. So let's go to the extract one more time. Right here. Extract. Oops. Okay, good. We're okay. Extract. Let's select, for example, these two layers we already did. So this one, and get the bag, and that one, and that one, that one. So this, that fellow, and that fellow. And I have to turn this thing around. There's 2 more on this side, and this and that. And then we say okay. And then we're going to join these 8. So there's the join. So I go from here to here and then say okay. And this one is going to be your uh, uh, 16 millimeters. So right click properties, 16 millimeters, 16 mm. Good. And I go and do the rest. So the next one is going to be actually extracting 5 times 4, 20 surfaces. This is why I rather stop it and go and do it. When I get to the top, I'll skip the 15 and 14, and then we do together 13 and 15 millimeter, okay? So let me stop this. Okay, now I'm down to the one that's 13 millimeters. That's these two. Okay, so we go to extract, the bag. Turn around. All right, so that's 8. Very good. I'm going to join from here to here and say OK. I'm going to rename this thing properties, or modify the name so that it says 14 mm. Sorry, this is 13 mm. All right, good. And finally, the very last one, namely this, the flange actually. So we go to where is the extract? Extract. There's 4 of them. This went into a state of coma. It's going to come back. Not to worry. Okay, so I want these four patches from the flange. Very good. Say okay. I'm going to join these from here to here. I'm going to join. And I'm going to call this thing 50 millimeter. That's the last one. Properties 50 mm. Say okay. Let's do a quick save here. All right, now why don't we apply our material to this? So let's go to tools. Here's tools. Here's a material. Let's create one. Create a material, and I'm going to call this thing December 7. Easiest. December 7, 2025. Simulation domain must be checked here. We say okay. Now we can apply it, and then we're going to put our material to it. So here it is. So we say apply. I don't need this. Close it. I'm going to apply it to the entire thing. We go down here, and we put down numbers. Okay. So structure. General option, density. I need the density because the weight of the tower is used. So 7850 kilogram per meter cube. That's density of steel. And then we go to Abacus Multiphysics, mechanical, elasticity, elastic. You see now, this was 210 GPa for the Young's modulus. Poisson ratio 0.3. Okay. And then we go to plasticity, metal plasticity, plastic right there. And yeah, so let's go ahead, find out what the numbers were. It was right here, oops, right there. 345 MPa, 0. That's the yield strength basically. 345 MPa, 0, and then 346 MPa. Now, as I said, oops, try it again. 346 MPa. Oops, wait a minute. MPa. Yeah. There we are. And here, Wagner uses or some dummy number 10 million. It really doesn't matter. Or 1 million, I'll use the same thing. It really totally meaningless. It's just to give it a slight tilt. And then we say, okay. Good. Do a quick save here. Okay, now we are ready to go and create our mesh. Now, before I go there, actually, let me go and create 2 points, one up there, one down below. Let me go to part design one more time, or actually, yeah, go to the 3D shape, which is generate shape design. And I'm going to go to wireframe, a point. I use center of a circle. Center of a circle. I select that arc on the top. The circle is right there. There's the point. You can see that. Okay. There's a point that's created right there. And we say, okay, except that I want to give this thing a different name. So I'm going to call this thing properties. I'm going to call this thing loaded endpoint. Endpoint. Good. Okay, and let's do also one at the very bottom. That's going to be the clamped endpoint. So one more point. Select the center of a circle. Select this arc at the end. The point has been created here. Yeah, right there. You can see that. Say OK. And I'm going to call this thing clamped end properties, or call it clamped end point. Very good. Save. Okay, we are ready to go and mesh our stuff. So let's go there. We switch to what is that? Structural model creation. I want to make sure that this is recording. It is recording. Very good. And it's going to be an empty FEM. Good. So if you go to click on the mesh tab right there, the mesh tab, I'm going to use surface quad mesh. You select. So let's start from the bottom and mesh all the way to the top. So from join 1 is the whole thing. I don't want it. Join 2 is the 17 millimeter. You select this. Remember, you want parabolic, 100 millimeter, okay? Nodes and mesh edges to be merged, okay? For the first one, it doesn't matter, but I'll check this thing for all of them. And then 10 millimeter, etc. Let me make sure that this is what we had here in my slide. Let's go down there. Yeah, everything is this. You can see that. And I'm going to call this thing, by the way, I'm going to call this thing 17 millimeter. 17 millimeter, so that I remember what this thing was. 17 millimeter. So mesh, don't forget to click on the mesh here. And then OK. So what happens is that this bottom one is mesh. Now, the fact that I say merge the nodes means that when I mesh the top one, all the nodes that are within 10 millimeter of these bottom nodes are going to get meshed. So let's do another one. Here is surface mesh, surface quad mesh. Let's take the 16 millimeter right there. Click here. Again, these are all the same, 100 millimeter, 10 millimeter tolerance. That's okay, mesh. And then we say, okay, notice that there will be no duplicate node. Actually, I'll show you that later. Okay, but actually we can see it here too. Let's see. For example, if I go to display, show me the nodes. That's okay. Say update. Show me the node numbers. For example, if you look at there's the seam, you can see that. If you come from the top, this node is 10. If you come from the bottom, this node is 10. That's good. That's good. All right, so let's get out of this. We go proceed with the rest of the stuff. We go to mesh one more time, quad mesh, surface quad mesh. And the next one is going to be, we just did 16. We're going to go do the 15 millimeter. Everything is the same. Mesh it and call this thing 15 millimeter so that we can distinguish meshes, different meshes. Good. Let's move on. Next one. Another one. 14 millimeter right there. I'm going to call this thing 14 mm. Mesh it. And then we say, okay. Oops. Let's go down here. 13. 13 mm. Everything's the same. Mesh it. Let me say okay. And finally, the last one, that's going to be a 50 millimeter one right there. I'll put down 50 millimeter. Okay, mesh. And then we say, okay. And once again, if you zoom in and you come from the top or the bottom and use the, let me update first of all. Go to display, numbering, come from the top. This node is 15,000 something. Go from the bottom, 15,000 something. Okay. Very good. So let me do a quick save here. Good. So now we're going to go define the section properties. So go to properties tab here. Here is the cell section. So this way we can start with the join. For example, this one, this is 17 millimeter. I put down 17 millimeter here. Material is correctly picked. You can see that. And then we say, okay. This is the next one. This was 16. We put down 16 millimeters. And this is 16 millimeter. So, okay. Now go to 15. 15 mm. I'll put down 15 mm here. 15 mm. We say okay. Now we go down to 14. 14 mm. Put down 14. Oops, 14. Yep. Then it's 13. I could have stopped the video because this is identical thing that I'm doing. But that's okay. Too late. 13 mm. And finally, this one, 50 mm underscore, and there's a value 15 millimeter there. You say, okay, let's do a quick save here. Now, before I go any further, I will create my connections here for the top point and the bottom point. Okay, so let's do that. So we go to the connections tab right there. See that, the connections tab? Here is the coupling, see that? Coupling. Now let's start with the top one. So remember, we created these points here. This is the loaded end coupling. You click on it. See that? All right. See for a second. Uh, First support is going to be point 1, loaded end point 1 right there. For the second support, I select okay, one thing I forgot to do here is, first of all, let me rename this thing. This coupling, I'm going to call it loaded end, loaded end, loaded end coupling. Okay. So for the support one, I selected that point, and for support two, I select these edges, these four edges. Now, if I don't see the four edges here, let's do the following. Let me hide the stuff, put the cursor here, put the cursor here, hide, hide. Okay, I'm having a problem there. So let me, oh, sorry, I forgot. Hang in there. For the support one, I select that point. Okay, good. Gee. For support two, actually, let me cancel that. Digging my own grave here. Let's try again. Coupling. For support one, I select the loaded endpoint. Good. For support two, what I have to do is to select these four edges. Okay, let me see. These four edges. So one edge, two edge. And if it's not letting you do that, just put the cursor there, hide, right click, hide, because there may be other stuff there, but that's okay. It's working. It's working. Good. All right. And I call this thing loaded end. All right. Go to distribute. Well, go to the coupling type, make it kinematic. All these are checked. You say okay. Good. Now do the same thing for the bottom. Okay, let's go to the bottom. So we go to the again connections tab. There we are, coupling. For the first, for name this thing to the clamped end. Clamped end. End coupling. For the first support, select the point at the very bottom. Left double click on it. For the support, you select these four edges. Make sure you select the very bottom four edges. One, two, around. Can I take it from here? Yeah. 3 and 4. Be careful because over here there are two curves very close to each other. So I want this bottom. Yeah, okay, good. And then again, make it kinematic. All of these are checked. We say okay. Excellent. So we have done whatever we needed to do in uh, structure model creation. So let me quickly save this thing. Okay, now we're going to switch application. We're going to go to mechanical scenario creation, and this is your FEA module. You can also go down here, structural scenario creation. These are both finite elements, same thing, except that this is a more elaborate version. So this is a modified, stripped down version of some features. For example, you can't do, to the best of my knowledge, as I recall, you can't do explicit calculation, finite element calculation here, but you can do it up there. Anyway, we're going to go to mechanical scenario creation. You click on it. All right, so we're going to do structural analysis, and we already created a mesh here, right here, finite element model. We already created that by meshing, by applying section properties, etc. Good. Okay. So first thing we're going to do is a static analysis. So we go to procedure, static. Notice that there is static and the static rigs. The YouTuber, Dr. Wagner, uses static step. In the paper, they're saying that they're using static rig step. Now, I'm not sure why one is doing one way The other one is a different way. I'll go with the YouTube version. So static step. You click on it. Now what you see here is exactly the slide that I showed you there. First of all, I put these numbers, the 0.01, 0.005, and 0.1. 0.01 initial time increment. What was that? 0.005, I think. Is that right? Hang in there. Let's check. Yeah, 0.005. And for the maximum time increment, I put down 0.1. And do not forget to go to the advanced and uncheck this, because if you're doing only material nonlinearity, no geometric nonlinearity, this should not be on. Uncheck. So now we've got exactly what we have over here. And then we say, okay. All right, so let's see now. We have to apply our boundary conditions and your load. So, okay. So first of all, if you don't want to see some stuff, you can use the filter, right-click, visibility manager. If I don't want to see my finite element model, for example, I say, don't show me this, just show me the model. Okay. Notice that these couplings are showing. If you don't want to see that, I want to see it, but if I don't want to see it, just click on that also. But that's okay. I want it. I want to be able to see it. Okay. Now, boundary conditions. Clamp. Clamp boundary conditions right there. Clamp boundary condition. Okay. And you can select from it either this this coupling that you see here, or from the tree, whatever is more appropriate. So let me see where I can find in the tree. Under engineering connection, remember the two couplings that are created? This is the clamped end right here. So make sure you select it, say okay. Good, good. Now the loads. First of all, gravity right there, gravity. When this is read into the software, this is how the coordinate system looks like. Okay, so in the negative y direction, make this thing 0. In the negative y direction, minus 9.81. Now, if I had constructed this thing myself in 3DEXPERIENCE, I would have made sure that this direction is z. But I imported the uh, step files directly, so it did whatever it wanted to. But anyway, so it's going to be gravity that acts in the negative y direction. We say okay. Now we're going to apply our loads. Okay. So here's the situation. First of all, let's apply our force in the negative y direction. So I'll put down V. Now, what is this? This is the name of it. Okay, so what is that? It was this force. Now, I'm using 8 meganewton. 8 meganewton. Okay, 8 meganewton. I'm using 8 meganewton. In fact, in Wagner's YouTube, he's using 10 times that, but it really doesn't matter. It's used because after all, I'm not going to let it go all the way to the end. So I'll use negative 8 meganewtons. So we go here. I called it V. In the negative y direction, minus 8. Make sure you put e to the 6, right? E to the 6. Yeah, this is 8 meganewton. And you can see that actually I have to go and select the support. The support is the loaded end right there, because I haven't selected the support. See that? Downward. Say okay. Very good. All right. Now, let's see. Another one. in this direction, you see what are these things? X going to the right, okay? Z going down. So if I decide to go to the right by that much, you just have to be careful with what you're doing, because later on when you choose the what plot to what against what, you may have to adjust these to be negative. See that there's a negative sign here, stuff. You got to be careful about these things, but that's okay. So that's fine. So I'm going to go do a concentrated load. I'm going to call this thing Q. That means shear. The support is that loaded end right there. In the direction X, I use the double of what it is here. So 3.2 meganewton. Okay. So loaded end in the direction X, 3.2 e to the 6. Yeah. Very good. Okay. Now let's do our moment. So you click on this again. I'll put down moment M. Moment means we're going to be using these, and the way it is, by the look of it, we're going to fix that thing if it's not right. So in the Z direction, moment in the Z direction, double of this 60. Okay, 60. So 60 e to the 6. Let's make sure this is going to come out. And for the support is going to be that loaded end. Now it looks like when I did it like this, it's put a minus sign here so it looks exactly like the drawing is. Okay, it's going that way. Okay, and finally let me see for a second. Yeah, and finally the torque. Another one of these. I'll call this thing the torque, and the loaded end coupling, and it's in the Y direction. Let me see what I had here. It's 22 times 2 is 44 meganewton. 44 e to the 6. Let's see. Yeah. So this drawing, these loads are consistent with the thing that I have in there. Okay. Now, the only thing is that it may not be consistent with what I'm trying to plot here, but so far so good. Say okay. Let's do a quick save here. Now, I can run this thing, but before I do that, let me go ahead and find out what is it that I want to get. So I go to the output. You click on this output. See that? Output. There's some default output, but there's something that you can request. So I think output, let me cancel this thing. Outputs 1 and 2 are by default, some stuff that you get by default. That's one. This one, I want the deflection of that top point. Okay, so I'll call this thing output, or call top deflection. Top deflection. Okay. I don't want the whole model. What I can do is I can say by connections, and it's top loaded end coupling right there. Okay. And I gave it that name. Very good. And all I want is deflection, extra information about deflection up there. So translation is good. Yeah, that's good. Translation and rotation is good. Let me say okay. Another one, I'm going to call this thing, what do I call this thing? Bottom force or clamp force, bottom force. Okay. And once again, from what is that? From connections and the clamp end. And I don't want everything. I just want forces, reaction forces. That's good. Forces a moment. And I think that's pretty much it. Okay. Let's do a quick save. You will see that after it runs, I killed it very quickly to make sure that it is doing what I want. And then once I'm happy with it, I go and run it again. So I go to simulate. First of all, let's do this. Model and scenario check. Don't anticipate any problems. This one is simulation check. You can take your chances and skip these, just run it, but it's helpful if there are any obvious fundamental mistakes. Say okay. Remember, initially it's going to be elastic. And by the way, while I'm doing this thing later on, I'm going to come and generate my plots too. Okay. Now that's not going to be the full run, but at least I can have access to those plots. I think this is going to go through too. We'll see. Let me tell you what I just said. This is not the full model that I'm going to run. Once I run it, I'm going to kill it right away. And then look at the deflection, everything looks good, and then generate the plot force deflection curve, because I want to keep it handy and available when I run it, and then eventually kill it at 83%. Okay. Yeah, this is almost done. It hasn't run yet. I haven't simulated it yet. These are all checks. Okay, good. No issue. Now, let me close that. Now I'm going to run it. Simulate. Simulate. This tower should lean to one side. And of course, at the initial stage, it's all elastic. Therefore, you're not going to see anything unexpected. It just kind of bends. That gives me some degree of confidence of everything is working. Then I'm going to go right there before I make the full run. I generate my graphs, make sure it is the kind of thing that I want, and then I'm going to run it. What I mean is try to generate these graphs for the, not completed model. This is going to go to iteration. The iteration of because of the material nonlinearity, not because of not because of geometric nonlinearities. But initially, everything is going to be elastic up to the point that yielding takes place, and then it moves on. So if I look at the iterations here, everything is going to be fairly fast and straightforward. Yeah. And then maybe in a few minutes, only minutes or so, I'm going to kill this job, make sure the results are okay. This is all elastic. I'm pretty sure it's all elastic. Okay, we can stop this thing. Let it go to maybe 40, 50, something like that. You see that there's a plot generated here too. This is the convergence plot, really. It's not, has nothing to do with the physical plot. Okay, I'm gonna maybe think, okay, yeah. Okay, so I'm gonna stop this, stop. It warns me that if I do that, I may lose some data, so that's fine, no problem. Say fine. Wait until it finishes. Nothing fancy is going to happen. It's just that the tower is going to lean to the direction I apply the shear force. Bend in that direction. Yeah, it's recovering the information before it actually kind of stops, and so that I can plot things. I don't want to say stop now, because if I say stop now, I won't have access to those half done results. And then once we're happy, we generate our 2D graph, then we're going to run it and let it go until 80%. Okay, so stopping the simulation after completing the increment. Fine. Okay. Now to see the results, half-baked results, you have to go and actually ask for it. It won't show you directly. Usually when these things finish, they take you to the post-processor, but because I stopped it, I have to go to the post processor myself. Okay, good. So we close this. Wait until this thing. Okay, close this. Nothing fancy. It doesn't show you any results. That's because I stopped it. So there is the results up to the point that I stopped it. For example, this is the initial one. Yeah, you see that? And if you look at the value of the stress here, it's below the yield strength probably. Yeah, this is 13. Yeah, 136 MPa. Okay, so up to this point that I killed it. This is the last one that I killed it. Okay, good. So let me close this. Let me close that. At least we know that it's going in the right direction. And then we're going to run it in a few minutes. Okay. So for generating plots, I'm going to go to 2D plot. See that? 2D plot. And I say XY plot from field. Okay. What do I want? Well, I want nodes, node set, but not all node set. I wanted the one that I created. Remember, this is going to be the let's do for example, the top one, deflection of the top, and that would be here, loaded and coupling. Okay, and I'm going to call this thing top displacement. Top displacement. Good. Now, what do I want? I want displacement, translation, in the direction x, direction 1, and I say, okay. So notice that the displacement increases. No problem. So I got my first graph right there on the results. On the results, 2D plot right there. Or another one. I go here. I'm going to call this thing force at the clamp. Force at the bottom. Or called bottom force. How about bottom force? Bottom force. What I want? Node sets. What do I want? The bottom clamped end coupling. I want not the stress, I want the reaction force in the direction 1. Then say okay. There we are. Very good. So let me close this thing. Now I want to put these together. In other words, I wanted to plot displacement, force versus displacement. So to do that, you have to go down here, XY plot. Oh, see, I already generated these two. XY plot from expression. And you select this, see that f of x, see the f of x? You select this. And then you select combine. Okay. So notice that two curves go in the combine. The first one is the horizontal axis, which is going to be displacement right there. You see this? You select this. The second one is going to be normalized force. So this is the force, but I want to normalize it. So I put it in parentheses here before I close the parentheses, divided by 16, what was that? 1.6, the applied shear. Uh, Remember, I normalized 1.6, 1.6 e to the 6. Okay. The only thing is that I have to put a negative sign for the force. So let's go ahead and see that. You go here, back here. I put a minus sign. Let's make sure this is correct. Minus. Okay. Good. Good. Excellent. Let me do a quick save. Oops. Wrong one. Yike. The save is right here. This is the save. Save. Now I'm going to run it, but I'll stop the video until around 85, 86%, and then we look at the result. I stop the recording. Just a second. This is all on the cloud. That's why it depends how fast the computer you've got, what connection you've got, connection speed you've got. So you're at the mercy of many things, or I am at the mercy of many things. Still trying to save. I stopped the recording. Oh, it's going. Excellent. So now we go back to scenario. Okay, everything is ready to go, and now we're going to run it again. Except that I'm not going to kill the job now. I'll kill it when it gets to 83, 84, 86%, something like that. Run it, everything is the same. Change anything, and say okay. And we monitor the iteration. Remember, up to 6%, 7% went very fast because it was really elastic analysis. Remember, it's 1:45 p.m. right now, 1:45. Okay, 1:45. So that when I stop the recording, we come back and we kill it. At that point, we know exactly what it is. 1:45. Let me write it down here. 1:45. iteration. So you're going to go very fast for a while, and then it it really slows down, and it doing the plastic stuff. So I'm gonna stop this because you've already seen this thing up to 0.7, but I'm gonna come and do it later, do the recording later. Yeah, so I'm gonna stop it. Okay, so I started at 1:45, and this is about 17, 18 minutes. It's kind of stuck at this point. I'm gonna kill the job now. Hopefully I don't have to make any adjustments to my 2D graph. We'll see. Trying to stop and recover whatever data that it has up to that point. But you see, yeah, that legend on the right disappeared because that was from the previous stop. We say, okay, now, first of all, let's go to the results. You have to go to the results here because you stopped it. Otherwise, you would have gone there automatically. There we are. And this is initially, and then gradually elastic, elastic. Okay, so remember the yield strength was 345 megapascal, so it's 87 right now. Yeah, this is 580, so it is gone plastic. And then you can see there is stuff happening down here. You can see that right there. Yeah, okay. And of course, this is stock plastic. Now, let me stop this and go to my 2D plot. This thing on the side, 2D plot, and then say OK. And there we are. This graph is, let me see if I can minimize this, is basically, let me see if I can put them side by side. May not be able to do that, but okay, so yeah, let me move this thing on the side. Yeah, we are dealing with load case 2, so it's that ash curve. Notice that it becomes asymptotically to around 1.8889. You can see that asymptotically becomes that at around maybe, I don't know, this is 1100 millimeter. Yeah, somewhere 1100 millimeter. So this graph fairly closely follows that graph. And that's really what I wanted to do. Now, if I had done load case 1, I would have got this, and this is all under nonlinear material only. All right, folks, that was a lot of work. Good luck.